So this talk is based on a joint work with Mauro Mariani and Etienne Pardoux on a theoretical foundation for the notion of metastability in the Müller's ratchet model. What I present briefly here is a part related to the asymptotic comparison of clicking ability. Well, I will talk also about asymptotic comparison of survival. So first, I introduce both the model of the Müller ratchet and the notion of asymptotic comparison, general notion of asymptotic comparison of survival, and give a few hints of the proof in the simplest case of the Müller ratchet for this comparison of clicking ability. So we are interested in the Müller ratchet in the emergence of deleterious mutation in a population, and more specifically in the events of fixation of these deleterious mutations, where you have an asexual reproduction mode. And the question is about the efficiency of the regulation with this asexual reproduction mode. So here we look for a simplified description, so we only consider deleterious mutations, and we assume that the offspring number is given simply through the number of mutations carried by the parent. So this is a random distribution, but with only this dependency. And we assume that at each generation we can have new deleterious mutations that add to the offspring. And here we look for a notion of survival, which corresponds to the fact that the Müller ratchet has not clicked, meaning that you don't have still the time at which the last individual carrying no mutation has vanished without similar offspring, so without offspring without mutations. So at this time, every individual carries a mutation which corresponds to the notion of fixation in some sense. So here we look for the general notion of asymptotic comparison of survival. So in the Müller, it's to avoid confusion with the notion of survival. I talked about clicking ability, but it is the same with the notion of survival that I've introduced in this stochastic model. And I look at the probability of survival of this stochastic model up to time t, and asymptotically as time goes to infinity. And what I want to do is to compare different initial conditions and say that if I start with the reference measured zeta, I'm not so bad as compared to any other potential initial conditions, meaning that if I look at the ratio of with the supremum at any fixed time t and let t goes to infinity, then this ratio won't go to infinity, meaning that the survival from initial condition zeta is not that bad as compared to any other ones. So this asymptotic comparison of survival is a crucial step in the proof of quasi-stationarity. Quasi-stationarity means that if you look at the distribution of the stochastic process, so the marginal, at a large time, under the event that survival is still, well, the process has still survived, then you have that the distribution of the state is given by this distribution alpha, while the dependency on the initial condition is simply taken by this function h with an exponential decay independent of this current state or the initial state, so exponential decay. And so if you have these kinds of results, of course you will have the asymptotic comparison of survival, and it is a crucial step. So now I look in more detail of the models for the Müller ratchet to be able to tackle this notion. So the first setting is rather illustrative and much simpler. So it's a discrete case where you have a finite number of individuals, and this finite number n stays stable at each generation. So at each generation I let each offspring choose independently its parents with a probability that depends on the number of mutations carried by the parent. Here I assume that it's proportional to this term exponential minus alpha I, where I is the number of mutations carried by the parent. Of course, I have to renormalize, which depends on the global number of mutations carried. And I assume that the mutations from the parent are transmitted to the offspring and that new mutations are introduced as a Poisson number. But in the preprint metastability between the cliques of the Müller ratchet, the main interest is, in some sense, in a generalization of this model, kind of extension, which is infinite dimensional. In this extension, we consider small selective effects, meaning that alpha is going to 0, with a large number of generations to still have something observed. And we don't keep track, of course, of any of the individuals one by one, but simply of the proportion of individuals carrying I mutations for any potential number I. Since we look for a large number of generations, again, it means that the rate of mutations is assumed to be small, and in this regime, mutations only occur one by one. And we look finally for the large population limit to make this dependency in N disappear. And since we still want to see the cliques, we need to keep the demographic fluctuations in the model. So it's kind of a stochastic diffusion process, which is stated here, where the first part has to do with the selective effect. Deleterious mutations, so I deleterious mutation is seen with this factor I. This term is the average number of mutations in the population and makes the population size stable in this compensation. And we have the introduction of new mutations from the class I to the class A-1, so class A-1 gain and class A loses a bit. And we have the demographic fluctuations like in a Feller diffusion process, but in this infinite dimensional regime. So encoded by a family of mutually independent Brownian motions, so it's a continuous process. So how do we deal with the asymptotic comparison of clicking ability in this discrete model? So we have to control the ratio, and the thing is to start with the initial condition zeta and say that, let's first say that we can reach the state x, meaning that in finite time with a lower bounded probability we have reached this state x. Then with the Markov property we'll have that the survival from initial condition x will entail the one from condition zeta. So, well, actually, if you have survived from a time t, from x you have a survival for a time a bit larger from zeta, but at least for a time t. And it implies that whatever the finite set that you want to consider, if you take the supremum not over all initial conditions but over this finite set, you will have this asymptotic comparison of survival. And so if we want to tackle it generally, we have to go beyond finite set. And the thing with finite sets is that the number of mutations carried by one individual is necessarily uniformly bounded. So we look for the time at which you have such a bound, because if you have it, then you can, you only keep a finite number of states. And so we look for the first heating time of this kind of set, where saying that no individual has more than L mutation in this set. And we look for the first time the process get back into this set. And so we need to control the survival to say that this time to get to the favorable sets in some sense is sufficiently bounded, so is an exponential moment that is larger, so exponent larger, than what we would expect as a asymptotic rate of survival from the initial condition zeta. And then with these two arguments, we can conclude the proof generally. So in the infinite dimensional model, the idea relies on the same principle, except that you have a continuum of states. So you need to look for densities, but then in infinite dimension, it's not tractable. So you have to kind of truncate and gather all conditions with large number of mutations into a single class and say that these processes with the distinguishing the classes or not are kind of similar. And for this comparison, you really exploit much the criterion that I gave in this preprint, exponential quasi-ergodicity for processes with discontinuous trajectories. So here I thank you for your attention. I hope you will be interested in looking at this notion of metastability for the Müller ratchet. Thank you.